Batteries are a good source of DC electricity by conversion of chemical energy, but they are not inexhaustible and will become discharged after a period of time and need recharging. The primary source of electricity in an aircraft is always a generator or alternator, which is driven by the engine. In this lesson, we will look at how magnetism is used to convert mechanical energy into electrical energy in a simple direct current generator. In 1831, an Englishman, Michael Faraday, discovered that if a conductor is moved through a magnetic field, cutting through the lines of flux, an electromotive force, or EMF, is induced in the conductor. In the interests of historical accuracy, it should be pointed out that the American Joseph Henry made the same discovery at more or less the same time. An EMF is induced into a conductor for as long as the conductor keeps cutting through the field. If the conductor stops cutting through the lines of flux, the induced EMF ceases. It does not matter whether the conductor or the magnetic field is moved, as long as there is relative movement between the two. If, however, the conductor is moved parallel with the lines of magnetic flux, then no lines of flux are cut, and no EMF is induced. If the conductor is connected to a complete circuit, then a current will flow in the circuit in proportion to the induced EMF. This discovery led to the writing of Faraday's law, which states that when the magnetic flux through a conducting coil is made to vary, a voltage is set up. The magnitude of this induced voltage is proportional to the rate of change of flux. The simplest form of electrical generator consists of a fixed magnetic field produced by a permanent magnet, with a single loop or coil of wire rotating in the magnetic field. The closed circuit is made by attaching rotating ring-shaped conductors, known as slip rings, to both ends of the loop. The slip rings are in contact with stationary carbon brushes. Continuous contact between the slip rings and the brushes is maintained by spring pressure. The brushes are attached to cables, which form a closed circuit. An EMF is induced in the rotating loop by electromagnetic induction. The part of the generator in which the EMF is induced, in this case the rotating loop, is known as the armature. The magnetic field, in this case produced by the permanent magnet, is known as the field. The direction of the conventional current flow in the wire loop can be determined by using a rule known as Fleming's right-hand rule. As the name implies, this rule involves the use of your right hand. To use the rule, you hold your right hand with your thumb, first finger and second finger extended, as shown on the screen. Align your first finger with the magnetic field from the North Pole to the South Pole. Point your thumb in the direction of rotation of the loop. Your second finger will now be pointing in the direction of conventional current flow. In the example shown here, as you can see, the first finger is aligned with the field, and the thumb is pointing upward in the direction of rotation of the red half of the loop. The second finger is pointing out of the screen, indicating that the conventional current is flowing out of the red half of the loop. We will now take a look at our generator, as the armature rotates through 360 degrees to see what sort of voltage is produced. The angle between the direction of movement of the armature loop and the flux lines of the magnetic field is known as the phase angle. In the position shown here, the armature loop will initially be moving in parallel with the magnetic field, with a phase angle of 0 degrees, so no EMF will be induced. As the armature begins to rotate, the loop begins cutting the field at a small but increasing angle, and an EMF begins to be induced. As the armature loop approaches 90 degrees to the direction of the magnetic field, the maximum number of lines of flux are being intersected, and the EMF is at its maximum. Between 90 and 180 degrees, the number of lines of flux being cut by the armature loop reduces again, so the EMF reduces. At the 180 degree point, the loop is again moving in parallel with the magnetic field, so no EMF is being induced. As the armature loop moves around from the 180 degree point, it once again begins cutting through the field lines, but now in the opposite direction. So an increasing EMF is induced in the opposite or negative direction, until at the 270 degree point, the loop is cutting through the maximum number of flux lines, and the negative EMF is at a maximum. The EMF now begins to fall again until the circle is completed. The armature loop is again moving parallel to the field. The EMF is 0, and the cycle begins again. Mathematically, the induced EMF is directly proportional to the sine of the angle between the direction of movement of the armature loop and the magnetic field. The alternating voltage produced by this type of generator is known therefore as a sine wave output. The current flowing in the external circuit will be an alternating current, or AC. That is to say, the current will first flow one way, then change direction and flow the opposite way as the direction of the induced EMF changes. The magnitude of the induced voltage can be affected by three factors. They are the rate of cutting of the lines of flux. The faster they are cut, the greater will be the induced voltage. This is controlled by the speed of rotation of the generator. If the generator is being driven by the engine, then its speed of rotation will vary with that of the engine. The number of turns of wire on the armature coil. The more turns there are, the greater will be the induced voltage. This is, of course, fixed during manufacture. And the strength of the magnetic field. A coil of wire can be wrapped around the two poles of the field magnet. Passing a current through this coil will allow the magnetic field strength to be increased, and so increase the voltage output of the generator. This coil is known as the field coil, and by controlling the current flow through it, the strength of the magnetic field can be varied, and the voltage of the generator can be controlled at a fixed value, irrespective of the generator speed. We already know from the study of electromagnets that when a current flows, a magnetic field is formed around the conductor. Heinrich Lenz, a 19th century Russian physicist, wrote a law about the way in which this magnetic field acts when it is set up by the current produced by a generator. Lenz's law states that a change of flux through a closed circuit induces a voltage and sets up a current. The direction of this current is such that its magnetic field tends to oppose the force producing it. What this means is that when our loop or coil is rotated, the magnetic field produced by the current flow in the coil will oppose the rotation. The greater the current flow, the greater will be the opposition. What this means in terms of practical electrical generators is that as the current flow from a generator increases, the work required to rotate the generator also increases. The electrical current produced by a battery flows in one direction only. This is known as a direct current or DC electrical supply. To produce a DC output from the simple generator, it is required to change the alternating EMF induced into the armature to a DC output at the generator terminals. This is done by replacing the slip rings with a single split ring commutator. A split ring commutator is constructed of two halves of conductive material with insulating strips electrically separating each half of the ring. The armature is constructed with one end of the loop connected to one conductor of the split ring and the other end to the other one. The commutator rotates with the armature. Electrical continuity is achieved by the use of carbon brushes. As the armature rotates from 0 to 180 degrees, the positive brush is in contact with commutator segment A, and the negative brush is in contact with commutator segment B. As it rotates from 180 degrees to 360 degrees, the positive brush is in contact with commutator segment B, and the negative brush is in contact with commutator segment A. The result is that every 180 degrees, the armature terminals are reversed. This means that the voltage will now rise and fall from 0 to its maximum level in one direction only, and the current will flow in only one direction, giving a type of DC supply. That is the end of the lesson. Here are the main points you need to take from it. An electromotive force can be induced in a coil by causing it to cut through the lines of flux in a magnetic field. The magnitude of the induced EMF will vary with the rate of cutting of the lines of flux, with the strength of the magnetic field, and with the number of turns on the coil. A field coil is used to control the strength of the magnetic field in order to maintain the output voltage of the generator at a fixed value, irrespective of the drive speed. The output of a simple generator is alternating current, or AC. The output can be changed to direct current, or DC, by use of a commutator.